All right, ladies and gentlemen. So the exam results are out. If you care to hear me, you can. Otherwise, you can leave. Are you interested? Okay. Exam results are out. If you see any issues you want to discuss, feel free to stop by the lab and see Patrick first. Well, if you want to pick it up, first of all, they are down in the lab. If you have issues, you can talk to him first and then to me or both, but they are the ones who graded them. I think the average is a little lower than last year at this point, right, Patrick? Both homework and exams. The homework is low 80 or even upper 70s, while the test is lower 70, 71 or so. Which is what it is. If I don't have the distribution here, but if you look at the distribution, there's more than half of the class that is above average, but then there's quite a few who are very low in grade, and those are the ones who really should start paying a little more attention, I believe, or at least come to office hours. Go back to my first lecture. You have a book, you have the video lectures, you have office hours, and I haven't seen too many people coming, so there's obviously some that are struggling with simple concepts, in my opinion. I don't think the test was particularly difficult. You may have lost a few points here and there, but those who are at the the low end, really haven't done much. So see us before it's too late. I guess that's my only recommendation. You have a lot of extra credit you can get from STK, of course, but you don't want to keep going on that with that trend. I think that was the only, the second announcement, I changed my office hours, so they're still the same days, 1 to 2:30. I hope that still works. But again, I haven't seen many of you, so I'm assuming it works. I wasn't seeing anyone between 4 and 5:30, so I moved it. It makes my day also a little easier on other aspects. So those are the announcements. And we need to finish other angles. I'll pick up where we left off, and also we'll talk about angular velocity and how it's related to other angles. Because if you choose a set of coordinates, like you do for a point x, y, z, then you want to compute the rate of change of those coordinates and give them some meaning. In this case, it's the angular velocity. So I'm going to re-sketch here the 3 rotations we went through, the 3-1-3 sequence. So hopefully in the same single sketch. So we went, I'm going to drop the head. These are unit vectors, okay? The unit vectors of the coordinate axis x, y, z. This was fixed in ECI. And we imagined that the eccentricity vector was initially pointing as x, the h vector pointing like z, and we go through this sequence of single axis rotations to go to the final actual orientation of the orbital plane and the orbit in general. So we went through a first rotation that we called big omega, and these moved x and y in the same plane to x prime and y prime, and z prime is the same as z. Then this was the rotation type 3, then rotation type 1, angle I about x prime, which is also corresponding to x second, and z moves to some new location z second, and this angle is I. So this is omega, big omega here, this is big omega here, and y prime leaves the plane, the xy plane, and goes into some new configuration, y second, and this is also I, and it's a 3-1-3, again it's a 3-1-3 sequence, so z, x, again z, so the z second is going to correspond to the last final z, which is the direction of the angular momentum. The rotation is through an angle little omega this time, and you're going to have also x leaving the equatorial plane now. So let's see if I can do a better sketch this time to hopefully see that in 3D. So x second goes into some x third. This is little omega here. And y second as well moves to some new location, y third. Okay? And we said we have the following relationships: x prime, y prime, z prime is projected into the xyz basis through a matrix that we called R3 of big omega. You can go back and check how this matrix looks like. There's always a 0, 0, 1, 0, 0 somewhere, and then sines and cosines. No surprises there. X, y, and z. And the next rotation is projecting the unit vectors with the second through a matrix R1 of I, and this projects on the x prime, y prime, z prime. And finally, x third, y third, z third projects through another R3 type of matrix, but it's a function of little omega on, of course, x second, y second, z second. We've seen that. We also said the x third direction is the direction of my eccentricity vector, so that unit vector is somehow related to E, it's the direction of E. The z third is the direction of H. This doesn't mean it's equal to, it's just that these vectors give me the direction, the unit direction for those two vectors. And then also, if you ever needed this x second is the line, or x prime, doesn't matter, it's the line of nodes. Okay? And as you put all these together, x third, y third, z third is equal to R3 of little omega, R1 of I, R3, which is a function of big omega, x, y, z. Again, these are unit vectors. This is how this basis projects into that basis by using a 3-1-3 sequence. We'll probably look at a MATLAB code that symbolically does this multiplication of three matrices. You can do it by hands, but it's not really that terrible. But that's really not the point here. So have you all finished the uncollected homework 3? I hope so, because that will lead into homework 2 at some point. So as you've noticed in the solution, if you have finished it yourself and then you looked at my solution, at some point when I need to extract, for example, x third and z third, I have this matrix product assembled. There's really no x, y, z here. There is this product here, and you take the first raw to give you x third, the second to give you y third, the third to get to z third. Because again, these are unit axis projections. Does it make sense? So look at the solution. That's how I extract x third. Is basically the if you call this just R, the first row of R gives you how x third projects into x, y, z, of course, because they are the coefficients that go on x, y, and z, etc. Okay? Just explaining one line of code without projecting. If you want, we can look at it. But again, try to go from state vector to orbital parameters and vice versa by yourself, and then check the code. Now, I give you also how you project the position and velocity. There's really no point in repeating that. Now, as I said, what is the next step here is talking about angular velocity. If we want to really complete the discussion about Euler angles, because you guys told me you wanted to look at Euler angles from scratch. So if you imagine, you forget about the fact that we're looking at an orbit for a second, you can have a physical object, as we've done last time, moving in space, changing orientation with respect to the reference coordinate system x, y, z that could be attached to this room, and this object has the x third, y third, z third attached to it, and it's moving around, right? And at each particular configuration, you have three numbers that we can keep calling big omega, I, little omega. You can call them alpha, beta, gamma, I don't care, three angles. If you know it's a 3-1-3 sequence, each orientation corresponds to three numbers. And that's for a position in terms of attitude. But then you also want the rates. You want to express somehow how quickly this object is changing orientation. We don't do spacecraft attitude mechanics in this class. If we have time, maybe we'll do a little bit more than 0. But for now, we're not doing it. But it is good to finalize the discussion about ordered angles introducing the angular velocity. So how do I use these 3 angles to express omega, which is that vector that tells me how quickly this object is moving around? Again, if you're looking at a point and you're looking at its Cartesian coordinates, x, y, z, then you know that taking the rate of change of these 3, you get the velocity. It's not that simple with ordered angles. It's not that immediate. But that's basically what you want to do. And I hope everybody is clear with the issue of singularity that we discussed last time. That for each sequence, it doesn't matter if you do 3, 1, 3 or something else, you're going to have a problem when the second angle reaches a certain point. And we'll talk about that once I show you some MATLAB code at the end. So, but let's look at these objects. So basically, let's say that I have a reference frame A, and that is my starting, is the frame where I'm sitting and I'm observing an object moving. So I call that A, and X, Y, and Z are fixed in this basis here. And my rigid body, for example, that is moving around, that is changing orientation, I call it B. And its coordinate system is the one with the triple prime here, okay? So I want to find a way to express the angular velocity of B with respect to A as a function of those 3 angles, for example. So how do we do this? Before we even start, one refresher, a concept that you should really have from dynamics. We call this vector angular velocity, but where do you see it the first time? Where do you actually define? This is a vector that is something we create. We define it and we use it from that point on. Where do you see it for the first time? Isn't it here? That at some point, someone told you, I can express the rate of change of a vector seen by an observer B to the rate of change of the same vector seen by A by adding this additional cross product, and you make up this vector that you end up calling angular velocity. But it's just a made-up vector that really shouldn't be called, in principle, velocity. Not even angular, probably. But the bottom line is that there is no way that you can do the following. There is no vector, I don't know what I want to call it, C, whatever. Actually, you know what, I'm going to say any. There is no way that you can take a vector and take its rate of change with respect to any observer and get omega. In general, this is not possible. Because it's not a real velocity. It's not like you taking x, y, z and taking the rate of change and that's a well-defined vector. It is just a way to express how a reference frame, in this case A, is changing its orientation in time with respect to B. But the fact that it's called the velocity is a little bit of an abuse because you cannot in general define for a 3-dimensional rotation any vector whose rate of change in time with respect to whatever observer you want to pick will give you this identity. It works for single axis rotations, but in general it doesn't work. So it is called angular velocity, we'll call it angular velocity, but it doesn't have the same physical meaning we give to a linear velocity for a point mass, for example. Do you remember all these things? Hope so. Still, I have to find this, because the angular velocity vector, even though it's an abuse to be called that way, it's important and we use it all the time. So how would you do it? Again, that object B is carrying around this basis, x triple prime, y triple prime, z triple prime, and I am sitting here in A, and I want to express that omega vector in terms of those 3 angles. Any ideas? I don't need this. No ideas? No? Try again. I know you've seen this stuff somewhere. Any memory at least? No? No hints? Nothing? Okay. Well, you go through the same procedure we just refreshed here. You go through single axis rotations, because we have a beautiful property of the angular velocity, which is the chain rule. If you have intermediate reference frames, you can add the angular velocities and get the angular velocity of the last with respect to the first. In other words, if I call, let's see, I've used A and B. Let's say that I define a reference frame C, and its coordinate system is x prime, y prime, z prime. Again, it doesn't have to be a real body, but I just define it that way, right? I imagine that this basis is fixed in C, and then another one, D, which has the following coordinate system. Well, then I can definitely say this. I can say that, I need to be careful here, that the angular velocity of B with respect to A, forget about this, okay? I've done A with respect to B. That theorem can be, of course, swapped with the order. But in this case, I'm looking at B and I'm seeing A. I can express these as what? Right. Okay, so C is the closest to A. Then what's next? You sure? Right. D and C always go like this, right? You're jumping from a letter to another. I know it's a terrible way of doing it, but B, D, done. This is valid, right? I can do this. This is a chain rule. Now, I think I can break those pieces down into single rotations. They are single rotations. What is the angular velocity of C with respect to A? Is the basis with the prime that has only, basically, that object has only rotated about the z-axis. So it's big omega dot, bless you, let's say just z prime. That's right, huh? Do we see that? Now, I know that these are unit vectors, and I have completely ignored to put underlines here. But maybe here I should, or maybe a hat. Just remember, they are all unit vectors. Okay, that's the first one. Then C, okay, let's see, D in C. D is hopefully the one with the, yes, the double prime with respect to C, this one. So it's the next movement, which was a rotation about this axis through an angle I. So it's an I dot. And I don't really know how I want to write that. I guess two dots like this. This is bigger. About which axis? X prime or x second. Which one do you want? X second. Doesn't matter. They're the same. Plus BD. B is the last one. It's the last movement which happened about this axis, little omega. There's an underline here. It's a unit vector. Little omega dot z third. Agree with that? So this is already a perfectly fine expression of the angular velocity of the rigid body B with respect to A, expressed in terms of the time derivatives of those angles. Here I should have been, well, this is generic, but you will see that this is actually a function of the angles and their time derivatives as well, but I didn't know that at this stage. So, but for now, I see the angles. They're time derivatives, but that's okay. They're there. I could stop there. There's nothing wrong with that expression. The vectors are belonging to different bases, but that's not illegal. What would you like to do, though? Do you like it that way? No? Why? What happens in reality? What do you think happens on a spacecraft? Let's forget about all these equations for a second. And you're flying a satellite, and this satellite is orbiting the Earth at whatever altitude. Maybe it's the ISS or something in that orbit, and it needs to point the camera down, and maybe it's body mounted. It's rigid with the body, so the entire satellite has to move around to point the camera, right? How do you think the angular velocity of that object changing orientation is measured? Where is it measured? Where do you measure your speed on your vehicle? Do you measure it on the car, or do you have a guy on the side of the road who's measuring your speed? You look at it on your car, right? On your vehicle. You have a way to measure your speed on board. So what is actually done is that there are devices on board the satellites, accelerometers, to sense accelerations, linear accelerations, and gyroscopes of different types that give you actually angular rates. So they're measured on board, of course. And so which basis do I want to use? So basically I want to go to one basis that is the same. I don't want mixed basis for practical reasons, and it has to be the one attached to the body. Which one is attached to the body? Is the triple prime. Okay, so let's transform these. I'll just invert a few of the expressions that I have there. Let's see, for example, this one. Remember that this is equivalent to x prime. So let's see, I have here that the basis with the prime is R1 inverse of I, x second, y second, z second, for example. So I'm taking this one, just inverting that relationship. Then what else do I need? I need x second, y second, z second, which is equal to R3 inverse of little omega of the basis with the third, right? Is that enough? Nope. Combining these two, you get x prime, y prime, z prime, projected into the triple prime by multiplying those matrices. So R1 minus 1, R3 minus 1 of little omega, and finally the basis with the third. So from here, let's see what I need. From here you can get x prime, which is the same as x second. So basically the first row of this product here of these two inverse matrices will give you what goes in here. And from the last one you get z prime. And I'll give you the final result. It's something that we'll also see symbolically in MATLAB. And actually the next uncollected homework is doing the same with a different sequence. So it'll be good to see how I do it in MATLAB. But basically I have everything now to express that vector into the basis that is attached to B. Questions? This is how it's going to look like if you put it in a matrix form. Let's see, omega of B with respect to A, if you finally put it in a matrix form, is going to be this ugly expression here, sine of little omega, sine of the inclination. Again, I keep calling them inclination maybe, and I shouldn't, because these are, for now, they're just three angles. They don't have to be necessarily related to an orbit. Cosine of little omega, sine of the inclination, minus sine of little omega 0, cosine of I 0, 0. And here I have big omega dot, I dot, little omega dot. And so this is equivalent to writing basically omega AB on the first axis, x triple prime, plus omega, B A on the second axis, y triple prime, plus, yeah. You see that? That's what I wanted to get. I just wrote it in a matrix form, but if you multiply this row times this column, you get this component. Second column, you get this component. Second column, you get this component. And this is the stuff that your gyroscope will measure. They are attached, they are devices physically attached to the spacecraft, and they can measure those numbers. Okay. So that is your final function. You see now, if you look at this assembly here, matrix times a column vector, now this is a function of the three Euler angles and their first time derivatives. And you would expect that. That angular velocity vector is expressing how fast and in which way B changes orientation with respect to A. So I was definitely expecting some rate of change, right, of the angles. Are we lost? Are we following? Okay. So now the mathematical trouble of singularity. Let's see. I I showed you what happens with the eraser, right? That you basically get the same orientation with infinite combinations. We said last time if the inclination is either 0, the second angle is 0 or 180, you have that issue. Now, it translates in math the moment you try to invert that matrix, for example. Because at the end of the day, what would you do on board your spacecraft? To know how you were pointing in space? Well, someone will probably give you some initial set of Euler angles. Somehow you have them. From a star tracker, some sensor gives you this. And then you have to integrate these differential equations in terms of the Euler angles. This is a 3-component vector measured on board. So you basically have to invert this matrix. Do we see that? So at some point you may want to have an expression like this equals whatever that matrix, what do we want to call that matrix? I don't know. Let's call it A, capital A. Inverse A that multiplies omega BA on the first axis, omega BA on the second axis, omega BA on the third axis. Again, these are given, measured. Somehow you have these from a device on board. You better know your initial orientation. And actually, in real space flight, every once in a while you get an update from star trackers or sun sensors or other devices that give you current attitude. So you can, every once in a while, get a refresh on this. But at the end of the day, you have to integrate these differential equations, like we've done in all the problems we've seen in MATLAB. It's just another set of differential equations, where this A to the minus 1 is just the inverse of this matrix, okay? Now, what happens when you invert a matrix? What is the first thing you do? I know MATLAB does it for you, but what would you do if you had to do it manually? I think, yeah, this is a 1, I'm sorry. Correct your notes, there was something missing. How would you go about computing the inverse of this matrix? Don't tell me you've never done it by hands. Once in your life, maybe? You compute the determinant first, right? How would you go about computing the determinant? I do this, I start from here, plus, minus, plus, minus, plus. Okay, I'm at 1. 1 is multiplying the determinant of this, which is minus sine squared, the sine of I, minus cosine squared, sine of I. Do we see that? So the determinant of A is plus, minus, plus, minus, plus. I think it's a minus sine of I, something like that. All right. And so when you invert the matrix, A to the minus 1 would be some stuff that you have to do up here that I'm not even going to bother doing. But definitely it's divided by the determinant, right? Remember that? Long time ago? So that's a problem. If I am at 0 and 180, that goes to 0, right? So here's another issue with singularities. A very clear mathematical issue that in principle you're dividing by 0. When you try to use these equations for the 3, 1, 3 sequence, and you try to integrate these differential equations for your 3 Euler angles, and you go through, you get close to 0, 180 for some reason, then it's, MATLAB is not going to crash on you because MATLAB will never see an exact 0. But in principle, you're doing something you should not be doing. So what do people do in these cases? Well, first of all, people don't use Euler angles on spacecraft. They use them on aircraft. They use them on rigid body, kind of rigid body vehicles that are not expected to go through a singularity. So you would choose a sequence, maybe a 3, 2, 1, something else, where if your aircraft goes through this kind of situation, everybody's basically dead. So it's not going to happen. Okay. So you're fine if you were to choose a 3, 2, 1 sequence, you can easily prove to yourself with the eraser exercise that 90 degrees for the second rotation is a problem. So imagine that if this is your aircraft and 90 degrees means something like this, you probably don't see these on a passenger's aircraft. You don't want to. So for those problems where you're never going close to the singularity, you're okay. But there are two ways to deal with this. One is you can switch representation. You can use the 3-1-3 sequence up to getting close to 0, 180, and then when you are, I don't know, at 5, 3 degrees, you're getting close, you're going in that direction, you switch, you use some other sequence where that problem is not there anymore. This is just an artifact. We choose that sequence. You can always switch. You can go from Cartesian coordinates to spherical coordinates to cylindrical coordinates. You can do whatever you want as long as you don't make mistakes with those conversions. The physical system that you're looking at is not going to change because you choose a different sequence. So people do that, they switch, or they use quaternions, which is something that will require 1 or 2 lectures, and I'll probably cover it this time. I don't usually. Maybe at the end of the class, of the semester. Because, I don't know, many of you will be in the capstone class in the fall. I'll probably be teaching that one. And if I do, we'll use quaternions for sure. So that's, it's a topic worth covering, but not for now. So this is really how you compute angular velocity with Euler angles, and it's the mathematical consequence of going through a singular rotation. Now, I want to show you the uncollected homework 4, which is really, really short, and has you playing with this. You basically reproduce what I have posted. I think I already put the code in Canvas. Basically, you're going to repeat a few things that I do here with a different sequence. What is a sequence 3, 2, 1? Just to, do we have time? Yeah. What if I wanted to go through represent the orientation of an object with a sequence 3, 2, 1? The line of thinking is the same, exactly the same. It's just that you do it by using different axes. So if I do a 3, 2, 1, you will start again from x, y, z. You do your first rotation. You can still call them big omega I and little omega, or alpha 1, alpha 2, alpha 3. I don't really care. So you still do this, okay? Go to x prime, y prime. Now what do? It's a 3, 2, 1. I use that axis right there, the second one in the sequence x, y, z, right? So the second rotation is actually happening about this axis, and we said I, right? So z is coming towards us somehow. I don't know how to represent that, but it's coming this way, and the x-axis is going into the plane below the equatorial plane, which is not easy to represent, but that's what's happening. Bless you. Okay, and so now it's the y prime that is equal to y second, and this is z second, and this is x second, and finally I rotate about that guy there, the little omega, which is going to move again my z somewhere else to z third, angle little omega, and yeah, the y is going to be somewhere else above the plane. You see that? Does it make sense? Any physical orientation except singular cases of this object in space, you can map it into a 3-1-3 sequence, 3-2-1 sequence, 1-2-3 sequence, 2-1-2. There are 12 combinations of these numbers that you can come up with. And prove to yourself with an object that if you go through 90 degrees, you are basically aligning the first and last rotation. They end up being the same physical axis, and you have the same problem that we've seen last time. Okay? So in the uncollected homework that I will project, I'm asking you to do some of this work that we have done with that sequence. Just change the sequence. It's a good exercise to really feel confident, I think, about using other angles. Do you have any questions? Is everything clear? Do you want me to go over any of these points? Again, it's just a way we represent how an object is oriented. Has its limitations. The beautiful aspect of all angles is that they are angles. I can see them. I can visualize them. For simple rotations, like single axis rotations, they're of course obvious. There are other ways to do it that are not that intuitive, but they don't have the singularity problem. Has anyone completed the other uncollected homework? No? Okay. Should give you some time. So So what I'm going to show you is just a symbolic MATLAB doing the calculation for this, well, I erased it, for the product of those three matrices. Okay. So this is just declaring a bunch of symbolic variables, rotation matrix 1 with an angle I, 3 little omega, rotation 3 big omega, the inclination angle, the big omega, the little omega, their time derivatives. I know they are long names, but you know. The angular velocity of B with respect to A, the matrix that I discussed with you, that one, and then its determinant, just to show, you know, symbolically that that's what's happening. So if I assemble the matrices R1, 2, and 3 as I've done last time, then you can express the prime basis. I've erased the middle board, but, and then, well, I simplify it, but that's what you get. This is the omega of B with respect to A. So go back to what I can probably rewrite it here. At some point I had this expression, right? X prime, Y prime, Z prime, which is equal to R1I inverse R3 little omega inverse X third, Y third, Z third. That is what I should have right there. When I do this, I compute this product. And well, this is just simplifying them, and then again, if you take the first row, you get x prime and all the other ones you need. So at the end of the day, I'm assembling this angular velocity. It's a combination of the three angles and their time derivatives. You can collect the time derivatives as I've done here and show that this is the matrix, which I'm actually putting together here. And well, nothing special. Simplify the matrix, compute the determinant is this minus the sign of inclination, so nothing special. So what I'm asking you to do is redo this with a 3-2-1 rotation. You just have to be careful in these intermediate steps. The matrices will be slightly different, but it's the same setup. So you can basically take this code and just change the lines you need to change. Is this making sense? Okay. And then what else? This is the old one, right? This is the uncollected tree, yeah. Then the next piece of that homework is actually integrating the inverse of those differential equations. So here I'm giving you, it's just an example. Say that I'm measuring on board the spacecraft, or somehow I know that the angular velocity vector, the three components of this one, are given as 0.01, 0.01 on the three-body axis. You can change those numbers, I don't really care. And that's your initial condition. I just call it y0, but those are the three Euler angles, initial values. And I am integrating the, I hope I'm integrating the this one, the 3, 1, 3. Yeah, it's a 3, 1, 3 sequence. So this function here implements this vector dot equals whatever is on the right hand side. That is what I'm implementing in this function. So it's outputting at the end big omega dot, I dot, and little omega dot. Okay? So that is the matrix, the inverse matrix that is actually computed right there. So I take these differential equations and I integrate them over time for 100 seconds in this case. And I haven't run this in a while, so I really don't know what's going to happen. Something. Did you run? Okay. Yeah. With the initial values I gave you and those omega values, these are your three Euler angles going up and down. That's how they behave. So play with this, change initial conditions. Try to see what happens if you actually plug in. I don't know what happens if you plug in a singular initial condition. I don't think it crashes. Unfortunately, that's the problem with software. It doesn't crash, but you need to know that this is not a good thing. It's not going to crash, is it? It did. That's great. Well, because I gave it a specific z. So at the very first time step, you actually had a divide by 0. So that's good. But so if you try to start where you know that you're going to go through a 0 or 180 somehow, my guess is that it's just going to continue to integrate, and it's it's not going to crash on you because it's not going to see exactly a 0. But you need, if you were to implement software on board the spacecraft, you will need to monitor, and you choose to do a 313, like in this case, you will have to monitor for how close you get with the second angle, being 0 or pi. So what I'm asking you to do here, hey, Valentine's Day, look at that. It's not today, right? Never know. You never know. We did 3, right? 4. So basically recreate the symbolic function that I just showed you, the main file that I just ran, and the differential equation function that was called by the integrator in the main file to go through a sequence 313. The 313 is posted. I put it on Canvas. So that's the simple exercise that I would like you to go through. Do you have any other questions about ordered angles? I think I've covered the main aspects and problems with ordered angles. Hopefully this is a good refresher for everybody. No?
So we only use them for orbits, right?
Well, no, you can use them for attitude of vehicles, of aerospace vehicles. In this class, I don't think we're going to use them much more than this, yeah. Unless I decide to do quaternions, then we'll see them again a little more. But that would be not orbital mechanics, it will be attitude mechanics, which I could do. If I have time, I'll probably do it. It's probably a good idea. No? So next time, I want to talk about ground tracks. Second homework last year was most of it about ground tracks. So we'll go over a few things and then probably look at that because it was very interesting. Okay, thank you.